Antarctica wasn't always frozen. For millions of years, it was covered in rainforests warmer than London. And now, it's starting to melt again. Picture this, February 2017. A research vessel is drilling through the seafloor off the coast of West Antarctica, pulling up sediment cores from 90 million years ago. The team is looking for clues about ancient ocean temperatures, expecting to find the usual suspects: marine microorganisms, mineral deposits, maybe some ancient shell fragments. Then they see something that shouldn't exist, something impossible. Tangled in the sediment, preserved for 90 million years under what is now one of the most inhospitable places on Earth, are roots. Plant roots. Not just any plants, these are roots from a temperate rainforest. Intertwined with them are fossilized pollen grains, spores from ancient ferns, and fragments of resin from coniferous trees. The kind of vegetation you'd find today in New Zealand or Chile, not beneath the ice sheets of Antarctica. The lead researcher, Professor Johan Klages from the Alfred Wegener Institute, stares at the sample under the microscope and realizes they've found something extraordinary. This isn't just evidence that Antarctica was once ice-free. This is proof that Antarctica was lush, green, covered in thriving rainforests, with a climate so mild that it could support complex ecosystems of plants and animals. But here's what makes this discovery truly mind-blowing. These fossils show that 90 million years ago, during the Cretaceous period, Antarctica had average temperatures of about 12–13 degrees Celsius. That's 54–55 degrees Fahrenheit. That's warmer than modern-day London, at a latitude where the sun doesn't rise for 4 months of winter. How is that even possible? How could a continent sitting at the South Pole, experiencing months of complete darkness, support a temperate rainforest? And what happened to transform this green paradise into the frozen wasteland we know today? This is the story of Antarctica's lost world, a story written in ancient rocks, fossil pollen, and ice cores. A story that takes us back to when dinosaurs still ruled the Earth, when the planet was so warm that there was no ice anywhere, when Antarctica was the furthest thing from the frozen desert it is today. This is a story about one of the most dramatic transformations in Earth's history: the freezing of an entire continent, the death of ecosystems that had thrived for millions of years, and a warning about what happens when Earth's climate shifts beyond certain tipping points. Before we dive into this lost world, I need you to understand something fundamental about our planet. Earth hasn't always looked like it does today. The continents have moved. The climate has swung wildly between greenhouse and icehouse states. And Antarctica, that frozen continent at the bottom of the world, has a history that's far stranger and more fascinating than most people realize. Today, Antarctica is defined by extremes. It's the coldest place on Earth, with the lowest temperature ever recorded, -89.2 degrees Celsius, -128.6 degrees Fahrenheit. It's the driest continent. The interior valleys receive less precipitation than the Sahara Desert. It's the windiest place, with katabatic winds screaming off the ice sheets at over 200 miles per hour. It's covered by ice sheets up to 3 miles thick, containing 70% of Earth's fresh water and 90% of Earth's ice. It's so hostile to life that only a few hardy species survive there. Some lichens and mosses clinging to exposed rocks, microscopic organisms in the soil, seals and penguins along the coasts, and not a single land mammal can survive its interior. No trees, no forests, no complex terrestrial ecosystems whatsoever. But this Antarctica, the one we know, is geologically young. The ice sheets that define modern Antarctica only formed around 34 million years ago. Before that, for hundreds of millions of years, Antarctica was radically different. And the evidence for this ancient, green Antarctica has been hiding beneath miles of ice, waiting to be discovered. The 2017 discovery wasn't the first hint that Antarctica had once been green. Scientists have known for decades that Antarctica must have been ice-free in the distant past. The evidence was there in the geology, in the fossil record, in the very existence of coal deposits beneath the ice, coal that could only form from ancient forests. But what the 2017 cores provided was unprecedented detail. These weren't just hints or fragmentary fossils. This was a snapshot of an entire ecosystem preserved in exquisite detail. The researchers could identify specific plant species, could reconstruct the structure of the ancient forest, could even estimate temperature and rainfall patterns. The sediment core revealed a world that seems almost impossible to imagine. A dense temperate rainforest, similar to the forests of modern New Zealand or southern Chile, trees reaching 20-30 meters high, 65-100 feet, a thick understory of ferns, shrubs, and flowering plants, a forest floor covered in decomposing plant matter, rich in nutrients, teeming with insects and small animals. The pollen analysis revealed over 65 different plant species in this single core sample. Conifers dominated, ancestors of modern southern hemisphere trees like podocarps and araucarias, but there were also flowering plants, ferns, and mosses. The diversity was remarkable, comparable to modern temperate rainforests. And this forest existed at about 82 degrees south latitude. To put that in perspective, that's just 8 degrees from the South Pole. Today, nothing grows there except for a few lichens in the very few ice-free areas. Yet 90 million years ago, it was a thriving rainforest. The researchers could even estimate how much it rained. Based on the types of plants present and the sediment characteristics, they calculated that this ancient Antarctic rainforest received about 1,101 for 00 millimeters, 4,355 inches of rainfall per year. That's similar to Seattle or London today. Not tropical monsoon levels, but plenty to support lush vegetation. But here's the puzzle that has climate scientists fascinated and, frankly, a bit worried. The amount of carbon dioxide in the atmosphere during the Cretaceous period has been estimated at roughly 1,140 parts per million ppm. That's about 2.5 to 3.5 times higher than today's levels of around 420 ppm. High CO2 creates a greenhouse effect, warming the planet. But even accounting for that extra greenhouse warming, climate models struggle to explain how Antarctica could be so warm. The models can get the tropics right, can get the mid-latitudes reasonable, but they consistently underestimate how warm the poles would have been. There's something missing in our understanding of how Earth's climate system works at such high CO2 levels. This matters because we are currently increasing atmospheric CO2 at an unprecedented rate. We're conducting an experiment on Earth's climate system, pushing it toward conditions that haven't existed for tens of millions of years. And if our models can't accurately predict what happened when CO2 was last this high, how confident can we be about what will happen as we continue to pump greenhouse gases into the atmosphere? But I'm getting ahead of myself. Before we worry about the future, we need to understand the past. We need to journey back 90 million years to the Cretaceous period, to a world so different from today that it would be almost unrecognizable. A world without ice caps. A world where dinosaurs still dominated the land. A world where Antarctica was green. In this investigation, we're going to explore that lost world in detail. We're going to walk through ancient Antarctic forests, meet the creatures that lived there, understand the climate that made it possible. Then, we're going to watch as that world ended, as the climate shifted, as ice began to form, and as millions of years of lush ecosystems were buried beneath miles of frozen water. We're going to use every tool available to modern science: fossil evidence, sediment cores, ice cores, climate models, plate tectonics, and atmospheric chemistry. We are going to piece together the story of Antarctica's transformation from one of the most complete climate records available anywhere on Earth. And we're going to ask the crucial questions: what turned Antarctica from a green paradise to a frozen wasteland? How long did the transformation take? Was it gradual or sudden? And most importantly, what does this tell us about how quickly Earth's climate can change? Before we continue, I want to hear from you. Drop a comment and tell me, can you imagine Antarctica covered in forests? Where are you watching from? There's something profound about people all over the world learning together about a time when one of Earth's most extreme environments was completely different. The story of green Antarctica is ultimately a story about Earth's climate system, how it works, how it changes, and how fragile the balance really is. It's a story that reaches back 90 million years, but has implications for our immediate future. Because here's the unsettling truth: the processes that froze Antarctica can work in reverse. And in some parts of West Antarctica, they already are. The ice is melting. The forests are long dead, but their fossils are being exposed as glaciers retreat. We are watching in real time as Antarctica begins to reveal the secrets buried beneath its ice. The frozen continent is starting to remember what it once was, and that memory should terrify us. Let's begin our journey to the lost world beneath the ice. Let's discover what Antarctica was before the freeze and understand what it took to transform an entire continent into the frozen desert we know today. The green Antarctica is waiting to be found. To understand green Antarctica, we first need to understand the world it existed in. Because 90 million years ago, during the late Cretaceous period, Earth was a fundamentally different planet. Not just in terms of which animals lived where or what the continents looked like, but in its most basic climate state. Earth had no ice. None. Zero. Not at the North Pole, not at the South Pole, not on mountaintops. The planet was completely ice-free from pole to pole. This is called a greenhouse Earth state, and it's dramatically different from the icehouse Earth we've lived in for the past 34 million years. Let me put this in perspective. Today, ice covers about 10% of Earth's land surface. The Antarctic ice sheet alone contains 26.5 million cubic kilometers of ice. The Greenland ice sheet adds another 2.85 million cubic kilometers. Mountain glaciers worldwide add more. All this ice reflects sunlight back into space, helps regulate global temperatures, and drives ocean circulation patterns that affect the entire planet. Remove all that ice, and you get a completely different Earth. A warmer Earth, a wetter Earth, an Earth where sea levels are 70 meters, 230 feet, higher than today, drowning most coastal areas. An Earth where ocean circulation works differently, where atmospheric patterns are fundamentally altered, where life exists in forms and places we can barely imagine. This is the Earth of the Cretaceous period, and it's the Earth we need to understand if we want to comprehend how Antarctica could support rainforests. Let's start with the continents, because they were in very different positions 90 million years ago. The supercontinent Pangaea had broken apart about 100 million years earlier, and the fragments were still drifting toward their modern positions, but they weren't there yet. South America and Africa were still relatively close together, having only recently separated. The South Atlantic Ocean was much narrower than today, more like a wide river than an ocean. India was an island continent, floating north toward its eventual collision with Asia, which wouldn't happen for another 40 million years. Australia was still connected to Antarctica, though the connection was beginning to weaken. And Antarctica sat roughly where it sits today, centered over the South Pole, but it looked completely different. It was part of a larger landmass that included Australia, and together they formed a substantial continent. More importantly, Antarctica's position relative to other continents created ocean circulation patterns that were radically different from today. Ocean currents are crucial to understanding climate. Today, Antarctica is surrounded by the Antarctic Circumpolar Current, a massive river of water that flows clockwise around the continent, isolating it from warmer waters to the north. This current acts like a barrier, keeping warm water away from Antarctica and helping maintain its frozen state. But 90 million years ago, this current didn't exist. Antarctica was still connected to Australia on one side and relatively close to South America on the other. Warm ocean currents from the tropics could reach Antarctica directly. There was no circumpolar circulation to isolate it. The ocean could deliver tropical heat right to Antarctic shores. This made an enormous difference. Ocean currents are one of Earth's primary heat distribution mechanisms. The oceans move vast amounts of heat from the equator toward the poles. Today, the Antarctic Circumpolar Current blocks this heat transfer, but in the Cretaceous, warm water could flow freely to Antarctica, moderating its climate despite its polar position. Now let's talk about the atmosphere, because this is where things get really interesting. The Cretaceous atmosphere contained about 1,400 parts per million, ppm, of carbon dioxide. compared to the pre-industrial level of 280 ppm and today's level of around 420 ppm. Carbon dioxide is a greenhouse gas. It traps heat in the atmosphere by absorbing infrared radiation that would otherwise escape to space. More CO2 means more trapped heat, means a warmer planet. This is basic physics, and it's not controversial among scientists. With CO2 levels 3 to 4 times higher than pre-industrial levels, the Cretaceous Earth was in a strong greenhouse state. Global average temperatures were about 610 degrees Celsius, 1118 degrees Fahrenheit, warmer than today. The tropics were hot, though not much hotter than today, because there's a limit to how hot tropical regions can get before atmospheric dynamics create cooling mechanisms. But the poles were dramatically warmer. Here's something most people don't realize. Greenhouse warming doesn't affect all latitudes equally. It has the strongest effect at high latitudes. This phenomenon, called polar amplification, means that when you add greenhouse gases to the atmosphere, the poles warm much more than the tropics. Why? Several reasons. Ice and snow reflect sunlight, so when they melt, the darker land or ocean beneath absorbs more heat, creating a feedback loop. Water vapor, itself a greenhouse gas, increases more at high latitudes in a warmer climate. Atmospheric heat transport patterns change. The result is that polar regions warm 2 to 3 times faster than the global average. We are seeing this today. The Arctic is warming about twice as fast as the rest of the planet. But in the Cretaceous, with much higher CO2 levels, this polar amplification was extreme. While tropical temperatures might have been only 5 degrees Celsius warmer than today, polar temperatures were 20-30 degrees Celsius warmer. This is how you get temperate rainforests in Antarctica, not because the whole planet was scorching hot, but because the poles were disproportionately warmer than they are today. But there's still a problem, one that puzzles climate scientists: the darkness. Antarctica sits at the South Pole. During winter, the sun doesn't rise for months. Near the coast, where the fossil rainforest was found, there would be about 4 months of continuous darkness each year. How can a forest survive that? Modern forests at high latitudes, like the boreal forests of Siberia and Canada, experience long, dark winters, but those regions freeze during winter. The trees go dormant, dropping their leaves if they're deciduous, or simply shutting down metabolism if they're evergreen conifers and waiting for spring. But Antarctica's Cretaceous forest couldn't rely on this strategy entirely because the fossil evidence suggests evergreen vegetation. These trees kept their leaves year-round. They had to survive 4 months of darkness while remaining physiologically active. How did they do it? This is still being researched, but scientists have some ideas. First, the winter temperatures remained above freezing. The ocean currents and high atmospheric CO2 kept Antarctica surprisingly mild even during the dark months. Trees could remain metabolically active at low levels, living off stored energy from summer's photosynthesis. Second, the Cretaceous Antarctic forest might have had adaptations we don't see in any modern forest. Perhaps trees had unusually large energy reserves, storing massive amounts of sugars and starches during the sunny summer months to fuel survival during winter darkness. Perhaps they had exceptionally efficient metabolisms, able to operate at minimal energy expenditure for months. Third, and this is fascinating, the darkness wasn't absolute. During the transition periods, late autumn and early spring, there would be twilight, weeks or months of dim light, not enough for vigorous photosynthesis, but perhaps enough to supplement energy reserves. And during the summer, there would be 24-hour daylight, continuous sunshine for months, allowing trees to photosynthesize around the clock and build up enormous energy reserves. Modern Antarctic mosses and lichens use a similar strategy. During the brief summer, they photosynthesize frantically, storing energy. During winter, they go into near-complete dormancy. The Cretaceous forest trees probably did something similar, but on a much larger scale. The Cretaceous world was also wetter than today. Higher temperatures mean more evaporation from the oceans, which means more water vapor in the atmosphere, which means more rainfall. The hydrological cycle was supercharged. Computer models suggest that global precipitation was 20–30% higher than today. This extra moisture fell disproportionately at high latitudes and in coastal regions, exactly where the Antarctic rainforest was located. The combination of mild temperatures, thanks to ocean currents and greenhouse warming, abundant moisture, thanks to high evaporation and atmospheric circulation, and seasonal light patterns, intense summer sun, dark winters, created a unique environment. It was strange, unlike any modern ecosystem, but it was stable. It persisted for millions of years, and it supported a remarkable diversity of life. The Antarctic forests weren't alone. The entire Cretaceous world was lush and green. Forests covered most continents. Even the Arctic was forested. Fossil evidence shows temperate forests in northern Alaska, Canada, and Siberia. The planet was so warm and wet that forests could grow almost everywhere except the driest deserts. This was the peak of the Mesozoic era, the age of reptiles. Dinosaurs had diversified into an incredible array of forms and dominated every terrestrial ecosystem. In Antarctica, while we don't have as complete a fossil record as we'd like, we know dinosaurs lived there too. Fossil discoveries from Antarctica include ankylosaurs, armored dinosaurs, theropods, meat-eating dinosaurs related to T-Rex, and ornithopods, plant-eating dinosaurs similar to Iguanodon. There were pterosaurs flying through the skies, marine reptiles like plesiosaurs swimming in the surrounding oceans, and countless smaller creatures, mammals, lizards, amphibians, insects, that we'll probably never find fossils of but certainly existed. The Antarctic forest ecosystem would have been a complex web of life. The trees provided structure and food. Herbivorous dinosaurs browsed on foliage, cycads, and ferns. Carnivorous dinosaurs hunted the herbivores. Insects pollinated plants and decomposed dead material. Small mammals scurried through the undergrowth, probably nocturnal to avoid the dinosaurs. Pterosaurs soared above the canopy, hunting fish along the coasts. It was a functioning, thriving ecosystem. Not a marginal environment barely supporting life, but a rich and diverse biome that had existed for millions of years and would continue for millions more. But this world, this greenhouse Earth with its ice-free poles and global forests, was not permanent. Earth's climate is never static. It swings between greenhouse and icehouse states over geological time, driven by processes we're only beginning to understand. And 90 million years ago, unknown to the dinosaurs browsing in Antarctic forests, forces were already in motion that would eventually transform their green paradise into the frozen wasteland we know today. In our next section, we're going to explore what those forces were and how they would eventually doom Antarctica to freeze. Imagine you could step into that ancient Antarctic forest. What would you see? What would it feel like? Let's reconstruct this lost world using the fossil evidence, the sediment cores, and our understanding of similar modern ecosystems. You're standing on the Antarctic coast, roughly 82 degrees south latitude, 90 million years ago. It's summer, and the sun hasn't set in weeks. It's midnight, but the sun hangs low on the horizon, casting everything in golden, perpetual twilight. The temperature is around 15 degrees Celsius, 59 degrees Fahrenheit, cool but comfortable, like an autumn day in England. The forest stretches before you, dense and green. Towering conifers rise 20 to 30 meters, 65 to 100 feet. Above you, their needle-like leaves dark green and waxy. These aren't quite like modern pines or firs. They're southern hemisphere conifers, ancestors of trees that today only survive in New Zealand, Chile, and a few other southern hemisphere locations. Podocarps and araucarias dominate the canopy, their massive trunks covered in thick, rough bark. The understory is a tangle of ferns, some as tall as a person, their fronds creating a dense layer of vegetation. Tree ferns, similar to those in modern New Zealand rainforests, create their own subcanopy. Cycads, palm-like plants that were much more common during the Mesozoic, dot the forest floor, their stiff, waxy fronds spreading in rosettes. The ground itself is soft, covered in layers of decomposing plant matter, fallen needles, dead ferns, rotting logs. Mosses carpet everything, bright green and spongy. The air is humid, laden with moisture from the nearby ocean and from the forest itself, transpiring vast amounts of water through millions of leaves. And it's quiet, eerily quiet by modern forest standards. There are no bird songs. Birds exist in the Cretaceous, but they're small and rare, still competing with pterosaurs for aerial dominance. There are no mammal sounds. Mammals exist too, but they're tiny, shrew-like creatures that hide during the day. The soundscape is dominated by insects. The buzz of ancient beetles, the chirp of primitive crickets, the rustle of arthropods in the leaf litter. Then you hear something else, a low rumble. The ground trembles slightly, and through the ferns emerges something that makes you forget about the absence of birds. A dinosaur, not a massive one. This is Antarctica, where even during warm periods, the extreme seasonal light patterns probably limited how large, cold-blooded animals could grow. This is a mid-sized ornithopod, perhaps 4 meters, 13 feet long, walking on its hind legs, using its smaller front legs to strip leaves from low-hanging branches. It's covered not in scales, but in a fine coating of protofeathers, insulation against the cool temperatures that will come in a few months when the sun finally sets. The fossil record from Antarctica is frustratingly incomplete. Most of the continent is buried under miles of ice, making paleontological exploration nearly impossible. But we have found enough to piece together the outlines of the ecosystem, and we can make educated guesses based on what we know about similar environments and time periods elsewhere. The 2017 sediment core and others like it have given us a detailed picture of the plant community. Analysis of the fossilized pollen and plant remains revealed over 65 different plant species, which suggests a diverse, mature ecosystem. The dominant trees were conifers, specifically podocarps and araucarias, both groups that are still alive today in the southern hemisphere. Podocarps are fascinating trees. Today, they're found in New Zealand, Chile, Tasmania, and a few other locations, all places that once connected to Antarctica in the ancient supercontinent Gondwana. They have needle-like or scale-like leaves, produce small fleshy cones, and are incredibly hardy, able to survive in nutrient-poor soils and harsh conditions. In the Cretaceous Antarctic forest, they would have been the backbone of the ecosystem, the dominant canopy trees. Araucarias are equally interesting. The most famous modern species is the monkey puzzle tree from Chile, with its distinctive geometric arrangement of spiky leaves. Araucarias are ancient trees with a fossil record extending back to the Jurassic period. They're tough, slow-growing, and extremely long-lived. Some modern specimens are over 1,000 years old. In Antarctic forests, they would have been the giants, the oldest, largest trees, survivors of centuries of polar summers and winters. Below the conifer canopy, the understory was dominated by ferns. The sediment cores show spores from dozens of fern species. Some were tree ferns, growing 3-5 meters tall, 10-16 feet, their trunks covered in fibrous roots, their crowns spreading large fronds. Others were ground-covering ferns, creating dense thickets in clearings where enough light penetrated the canopy. Cycads were also present. These palm-like plants were far more diverse and widespread during the Mesozoic than they are today. They produce large, starchy seeds that would have been important food for herbivorous dinosaurs. In the Antarctic forest, cycads probably grew in the understory and in clearings. Their tough, waxy leaves adapted to survive both the bright summers and the dark winters. And then there were the flowering plants, angiosperms. The Cretaceous period was when flowering plants were just beginning their spectacular rise to dominance. In Antarctica, they were still relatively minor components of the flora, but they were there. Small herbaceous plants, shrubs, possibly some small trees. The pollen record shows their presence, though we don't know exactly which species. The forest floor would have been a world unto itself. Layers of decomposing organic matter, fungi breaking down dead wood and leaves, primitive insects and other arthropods living in the leaf litter. Millipedes, centipedes, ancient beetles, springtails, all the tiny creatures that process dead plant material and recycle nutrients. These organisms don't fossilize well, but they must have been present. No forest can function without decomposers. Now let's talk about the dinosaurs, because this is where Antarctica's polar location created unique challenges and unique adaptations. Dinosaurs were the dominant land animals during the Cretaceous, but Antarctica was not an easy place for them to live, even during the warm period. The extreme seasonal light cycle was the biggest challenge. During summer, 24-hour daylight meant unlimited time for feeding and growing, But during winter, months of darkness meant no plant growth. Herbivorous dinosaurs couldn't simply keep grazing year-round like they could at lower latitudes. They had to adapt. Some species probably migrated. When winter approached and the sun began setting for longer each day, herds of dinosaurs might have walked north, following the retreating summer into Australia or South America. Then in spring, they would return to Antarctica to exploit the explosion of plant growth during the long summer days. This is speculation, but it's supported by fossil evidence of similar dinosaur species found in both Antarctica and Australia, suggesting movement between the continents. Other species probably stayed year-round. These would have needed special adaptations. The protofeathers or simple feathers we see in many Cretaceous dinosaurs would have been crucial insulation during the cool, dark winters. These dinosaurs would have survived by eating stored fat reserves, slowing their metabolism, and perhaps hibernating or going into torpor, a state of reduced metabolic activity similar to what some modern reptiles and birds do. The Antarctic fossil record has yielded several significant dinosaur discoveries despite the difficulty of excavation. In the 1990s, paleontologists found the partial skeleton of an ankylosaur, an armored dinosaur built like a tank, covered in bony plates. This individual was about 4 meters, 13 feet long. Ankylosaurs were herbivores, slow-moving browsers that fed on low vegetation. Finding one in Antarctica confirms that even heavily armored, presumably cold-blooded dinosaurs could survive in polar environments. More exciting was the discovery of Cryolophosaurus elioti, the frozen crested lizard found in early Jurassic rocks of Antarctica. While this predator lived earlier than our 90-million-year-old forest, about 190 million years ago, it proves that even large carnivorous dinosaurs could thrive in Antarctica when conditions allowed. Cryolophosaurus was about 6 meters long, 20 feet, and had a distinctive forward-pointing crest on its head. It was a predator, which means there must have been prey animals, herbivorous dinosaurs, to support it. Small theropods, the group that includes T-Rex and eventually gave rise to birds, have also been found in Antarctic rocks. These were probably quick, agile hunters that preyed on smaller animals, primitive mammals, lizards, amphibians, juvenile dinosaurs. Pterosaurs soared through Antarctic skis. These flying reptiles ranged from tiny species the size of sparrows to giant forms with wingspans of 7 meters or more, 23 feet. They hunted fish in the coastal waters, insects in the forest, and possibly small terrestrial animals. Fossil pterosaur bones have been found in Antarctica, confirming their presence. In the seas surrounding Antarctica, marine reptiles ruled. Plesiosaurs, long-necked marine reptiles, swam in the Southern Ocean, hunting fish and squid. Mosasaurs, giant marine lizards, were apex predators, some reaching lengths of 15 meters, 50 feet. Fossil evidence of both groups has been found in Antarctic marine sediments. The mammals of the Antarctic forest were small, probably nocturnal, and frustratingly rare in the fossil record. During the Cretaceous, mammals were still subordinate to dinosaurs, occupying ecological niches that larger reptiles couldn't exploit. They were probably shrew-like or rat-like creatures, feeding on insects, seeds, and possibly dinosaur eggs. Their small size and nocturnal habits would have helped them survive the winter darkness. They could hibernate, live off stored fat, and their small size meant lower energy requirements. The forest ecosystem would have operated on a seasonal cycle, unlike anything in modern ecosystems. During the endless summer, productivity was off the charts. Plants photosynthesized 24 hours a day, growing rapidly, producing enormous amounts of leaves, seeds, and wood. Herbivorous dinosaurs gorged themselves, building up fat reserves. Carnivores hunted the fat, slow herbivores. Insects exploded in population. The entire ecosystem was frantically making use of the continuous light. Then, as autumn approached and the sun began setting for longer periods each day, everything changed. Plants stopped growing and entered dormancy. Herbivores that couldn't migrate faced months without fresh food. They would have lived off fat reserves, browsed on tough woody vegetation, possibly even eaten bark and dead plant material. Carnivores would have faced lean times, with fewer active prey animals. Many creatures probably entered torpor or hibernation states. Winter in the Antarctic forest would have been strange, not frozen, but dim and quiet. The temperature remained above freezing, thanks to the warm ocean currents and high atmospheric CO2, but with no sunlight for months, the forest was in suspended animation. Trees standing dormant, dinosaurs sleeping in burrows or caves. Only the most hardy creatures remaining active. Scavengers feeding on animals that died during the winter, decomposers slowly processing dead plant matter, perhaps some small mammals venturing out in the darkness. Then spring would arrive. The sun would return, first just for a few hours a day, then longer and longer until it never set at all. The forest would explode back to life, plants sprouting new growth, animals emerging from dormancy, migratory dinosaurs returning from the north. Within weeks, the forest would transform from a quiet, dim world to a frenzy of activity. This seasonal pattern continued for millions of years. The Antarctic forest was stable, mature, adapted to its unique environment. Life had found a way to thrive even at the South Pole, even with months of darkness, even in conditions unlike anywhere else on Earth. But this stability was an illusion. Deep beneath the surface, geological forces were building that would eventually doom the Antarctic forest. The continents were drifting, the climate was slowly changing, and millions of years in the future, the green paradise would become a white hell. The death of green Antarctica didn't happen suddenly. There was no catastrophic asteroid impact, no volcanic eruption that blotted out the sun, no single event that you could point to and say, that's when it ended. Instead, Antarctica froze slowly over millions of years, driven by processes so gradual that no single generation of plants or animals would have noticed the change. But over geological time, those tiny changes accumulated into a transformation so complete that it erased almost all evidence of the world that came before. Let's trace how it happened, step by inevitable step. The first domino to fall was continental drift. Earth's continents sit on massive tectonic plates that float on the semi-molten mantle beneath. These plates move incredibly slowly, typically just a few centimeters per year, about the rate your fingernails grow. But over millions of years, centimeters add up to thousands of kilometers. Continents split apart, oceans open, mountain ranges rise, and the geography of Earth is completely rewritten. Around 80 million years ago, about 10 million years after our snapshot of the Antarctic rainforest, the forces that would doom Antarctica began to accelerate. The supercontinent Gondwana, which had included South America, Africa, Antarctica, Australia, India, and Madagascar, was breaking apart. Africa and South America had already separated. India was drifting north on its collision course with Asia. And critically, Australia was beginning to pull away from Antarctica. This separation happened agonizingly slowly. The gap between Australia and Antarctica widened at perhaps 2-3 centimeters per year. At that rate, it would take millions of years to create a significant ocean gap, but geological time is patient. By about 45 million years ago, Australia had separated enough that a deep-water passage existed between the two continents. This doesn't sound dramatic, but it was perhaps the single most important event in Antarctica's climate history, because this gap allowed something new to form, the Antarctic circumpolar current. Let me explain why this matters. Ocean currents are driven by wind, by the rotation of the Earth, and by differences in water temperature and salinity. At the equator, the sun heats the water, making it warm and less dense. This warm water flows toward the poles. At the poles, the water cools, becomes denser, and sinks. This creates a global circulation pattern that moves heat from the tropics toward the poles. In the Cretaceous, with Antarctica still connected to or very close to other continents, warm tropical water could reach Antarctica directly. Currents flowing south from the Indian Ocean and Pacific Ocean delivered heat to Antarctic shores. This kept coastal Antarctica relatively mild despite its polar position. But once Australia separated and South America began pulling away, which happened later, around 35 million years ago, something changed. The circumpolar region around Antarctica became a continuous ring of ocean with no land barriers. And in this ring, wind patterns and Earth's rotation created a current that flows clockwise around Antarctica. the Antarctic Circumpolar Current. This current is absolutely massive. It's the largest ocean current on Earth, moving about 135 million cubic meters of water per second. That's more than 600 times the flow of the Amazon River, and it acts like a barrier, isolating Antarctica from warmer waters to the north. Think of it as a moat around a castle, but instead of keeping invaders out, it keeps warmth out. Warm tropical water flowing south hits the Antarctic Circumpolar Current and gets deflected, flowing east around Antarctica without ever reaching the continent. Meanwhile, the current mixes deep, cold water with surface water, creating a band of cold ocean surrounding Antarctica. Once this current fully formed, Antarctica's climate fate was sealed. Cut off from tropical heat delivery, the continent began to cool. But this took time. The current didn't appear overnight. It strengthened gradually as the gaps between continents widened, as ocean passages deepened, as wind patterns adjusted to the new geography. While this was happening, another process was simultaneously pushing Earth toward a colder state: the slow decline of atmospheric CO2. Remember, the Cretaceous greenhouse climate was maintained by high CO2 levels of 1,400 ppm. This CO2 acted like a blanket, trapping heat and keeping the entire planet warm. But CO2 levels don't stay constant. They're controlled by a complex balance between volcanic outgassing, which adds CO2 to the atmosphere, and weathering processes, which remove CO2. When rock is exposed to rain and chemical weathering, it reacts with CO2 from the atmosphere, eventually locking that carbon away in sediments and limestone. During the Cretaceous, volcanic activity was extremely high. The ocean floors were spreading rapidly as continents broke apart. Massive volcanic provinces formed in India, Madagascar, and elsewhere. All this volcanism pumped enormous amounts of CO2 into the atmosphere, maintaining the greenhouse climate. But by the Paleogene period, starting about 66 million years ago, after the dinosaurs went extinct, volcanic activity was declining. The rate of seafloor spreading was slowing. Meanwhile, weathering continued to remove CO2 from the atmosphere. The result was a slow, steady decline in atmospheric CO2 over tens of millions of years. By 50 million years ago, CO2 levels had dropped to perhaps 801,000 ppm. By 40 million years ago, maybe 600-800 ppm. By 34 million years ago, around 500-600 ppm. Each drop pushed Earth's climate a bit cooler, especially at the poles where greenhouse warming has its strongest effect. These two processes, continental drift isolating Antarctica and declining CO2 cooling the planet, worked together. Neither alone would have been sufficient to freeze Antarctica, but combined, they created unstoppable momentum toward an ice age. The fossil record from this transition period is frustratingly sparse. Antarctica was already difficult to access for paleontologists, and as ice began forming, it buried the evidence. But from the few sites we can access, and from cores drilled through sediments in the Southern Ocean, we can piece together the story. Around 50 million years ago, Antarctica was still largely forested. The climate had cooled somewhat from the Cretaceous peak. Average temperatures were perhaps 8-10 degrees Celsius instead of 12-13 degrees. But this was still warm enough for temperate forests. The dinosaurs were gone, wiped out by the asteroid impact 66 million years ago, but mammals had diversified to fill their ecological niches. Antarctic forests were now home to marsupials, primitive primates, and other mammals. By 45 million years ago, the cooling was becoming noticeable. The forests were changing composition. The most cold-sensitive species were dying out or retreating to warmer coastal areas. The remaining forests were dominated by the hardiest species: southern beeches, nothofagus, conifers, and tough shrubs. These were still forests, still green, but they were simpler, less diverse, adapted to increasingly harsh conditions. The first glaciers appeared in the mountains of Antarctica around 45-50 million years ago. These weren't ice sheets, they were alpine glaciers, similar to what you see in modern mountains. Snow fell at high elevations, accumulated year after year, compressed into ice, and flowed slowly down valleys. This was a critical threshold. Once glaciers exist, they create feedback loops that accelerate cooling. Ice reflects sunlight much more effectively than rock or vegetation. This is called the albedo effect. Dark forest absorbs about 90% of incoming sunlight, converting it to heat. White ice reflects about 80% of sunlight back to space. Replace forest with ice, and you've dramatically reduced the amount of solar energy the land surface absorbs. Additionally, glaciers affect local weather. Cold air flows off ice sheets like water flowing downhill, creating persistent high-pressure zones and suppressing precipitation. Less precipitation means less plant growth, which means more bare ground that can freeze and become ice. These feedback loops meant that once glaciation started, it tended to accelerate. Each glacier made the surrounding area colder and drier, making it easier for more glaciers to form. It was a runaway process. By 40 million years ago, the mountain glaciers in Antarctica were extensive. Ice covered the highest peaks and flowed down into lowland valleys, but the lowlands were still forested. The coasts were still relatively mild. Antarctica was a land of contrasts, icy mountains surrounded by green valleys. Then around 34 million years ago, something called the Eocene-Oligocene transition occurred. This was a relatively rapid, in geological terms, cooling event that lasted perhaps a few 100,000 years. Temperatures dropped sharply, CO2 levels fell below a critical threshold, and Antarctica crossed a tipping point. The ice that had been confined to mountains began spreading across the lowlands. Summer temperatures dropped below the point where ice would completely melt. Year after year, more snow fell than melted. The snow compressed into ice. The ice sheets began to grow. The forests didn't disappear all at once. They retreated, pushed back by the advancing ice. The coldest valleys froze first, then the coastal lowlands, then even the warmest refuges. Tree line moved northward as temperatures dropped. Species died out or retreated to warmer continents via land bridges that still existed. For millions of years, Antarctica had been home to rich, complex ecosystems, forests full of life, animals adapted to the unique polar environment, an entire world that had thrived for tens of millions of years, and in perhaps just a few 100,000 years, a geological instant, it was gone. By 34 million years ago, permanent ice sheets covered most of Antarctica. The forests were dead, buried under growing ice. The animals were extinct or had fled to Australia and South America. The green continent had become white. But even then, Antarctica wasn't as frozen as it is today. The ice sheets of 34 million years ago were smaller, more dynamic. They advanced and retreated with climate fluctuations. Coastal areas remained ice-free during warmer periods. The transformation wasn't complete. In our next section, we're going to follow Antarctica through the final stages of its freezing. We're going to watch as the ice sheets grew to their modern size, as even the last ice-free refuges were covered, as Antarctica became the frozen desert we know today. And we're going to ask, could it ever reverse? Could Antarctica become green again? The ice sheets that formed 34 million years ago were just the beginning. Antarctica would continue to freeze, cool, and transform for millions more years until it reached the extreme state we see today. This is the story of how a continent went from partially frozen to the coldest, driest, most inhospitable place on Earth. After the initial glaciation 34 million years ago, Antarctica entered a period of dynamic ice sheet behavior. The ice sheets weren't stable. They grew during cold periods and shrank during warm periods. There were times, between about 34 and 14 million years ago, when parts of coastal Antarctica became ice-free again during particularly warm intervals. We know this from sediment cores drilled from the ocean floor around Antarctica. These cores contain layers of sediment that tell stories about what was happening on the continent. Some layers contain pollen from tundra vegetation, dwarf shrubs, grasses, and mosses. This means that even after the initial freeze, there were periods when plants could grow on Antarctica, when ice retreated enough to expose land, when summer temperatures rose above freezing. These weren't forests anymore. The trees were gone, never to return, but there was still life, hardy alpine and tundra plants that could survive in the brief summer growing season and endure months of winter darkness. These plants left their pollen in the sediments, proof that Antarctica oscillated between fully frozen and partially ice-free states for millions of years. But around 14 million years ago, something changed. The climate took another step toward colder conditions. The Antarctic ice sheets began growing again, larger and more permanent than before. By about 13-14 million years ago, the East Antarctic ice sheet, the larger of Antarctica's two major ice masses, reached approximately its modern extent. This ice sheet is staggering in scale. It covers an area larger than the United States and contains enough ice to raise global sea levels by about 53 meters, 174 feet, if it completely melted. The ice is up to 4.8 kilometers thick, 3 miles in some places. The sheer weight of the ice has pushed the bedrock beneath it down, creating deep basins that are actually below sea level despite being buried under miles of ice. The West Antarctic ice sheet, which covers the smaller western part of the continent, has a more complicated history. It's partially grounded on bedrock that lies below sea level, making it more vulnerable to melting than the East Antarctic ice sheet. The West Antarctic ice sheet didn't reach its full modern extent until more recently, perhaps 5-6 million years ago, and it has collapsed and reformed multiple times during warm periods over the past few million years. By the time both ice sheets reached their full modern extent, Antarctica was completely transformed. The continent that had been green, forested, and full of life was now buried under ice so thick that mountains were completely covered. Only the highest peaks of the Transantarctic Mountains and a few other ranges poked through the ice as nunataks, isolated rock islands in a sea of white. The climate became extreme beyond anything the continent had experienced before. Temperatures at the South Pole, which sits on top of a thick ice sheet at high elevation, plummeted. Today, the South Pole has an average annual temperature of -49 degrees Celsius, -56 degrees Fahrenheit. The coldest temperature ever recorded on Earth was at Russia's Vostok Station in Antarctica, -89.2 degrees Celsius, -128.6 degrees Fahrenheit, in July 1983. More recently, satellite measurements have detected even colder temperatures, down to -98 degrees Celsius, -144 degrees Fahrenheit, in small pockets of the East Antarctic Plateau. At these temperatures, which occur during the darkest part of winter in calm, clear conditions, carbon dioxide itself can freeze out of the atmosphere. The air becomes so cold it literally crystallizes. Antarctica also became the driest continent. The interior of Antarctica receives less than 2 inches of precipitation per year, less than the Sahara Desert. This seems counterintuitive. How can a place covered in ice be a desert? The answer is that the ice didn't form from local precipitation. It accumulated over millions of years from snowfall that, while minimal, never melted. Century after century, millennium after millennium, thin layers of snow compressed into ice, building up to the massive sheets we see today. The extreme cold creates unique atmospheric phenomena. Katabatic winds, gravity-driven winds that flow down from the ice sheet interior toward the coast, can reach speeds over 200 miles per hour. These are the strongest winds regularly experienced anywhere on Earth. The air at the high elevation interior cools and becomes dense, then flows downhill like an invisible avalanche, accelerating as it descends. Life on Antarctica became limited to the extreme hardiest organisms. On the continent itself, only lichens, mosses, and microscopic organisms survive in the few ice-free areas. These organisms don't just survive, they thrive in their own way, adapted to conditions that would kill almost any other life form on Earth. The most remarkable are the endolithic organisms, bacteria, algae, and fungi that live inside rocks. They colonize the tiny spaces between mineral grains in porous sandstone, where they're protected from the worst extremes of wind and cold. During summer, when sun warms the rock's surface, they photosynthesize and grow. During winter, they go dormant, surviving temperatures that would shatter their cells if they were exposed. Antarctica's lakes, yes, there are lakes, though most are frozen, harbor unique ecosystems. Lake Vostok, buried 4 kilometers, 2.5 miles beneath the ice sheet, is one of the world's largest lakes by volume. It's been isolated from the surface for perhaps 15 million years. Scientists have only recently been able to sample it, and they've found bacteria living in this ancient, dark, isolated environment. Life that has been completely cut off from the rest of Earth's biosphere for millions of years. But even more remarkable is what lies within the ice itself. As snow fell and compressed into ice over millions of years, it trapped tiny bubbles of ancient atmosphere. These bubbles are time capsules, preserving samples of Earth's atmosphere from hundreds of thousands of years ago. Ice cores drilled from Antarctica have revolutionized our understanding of Earth's climate history. The longest continuous ice core ever drilled extends back 800,000 years. In that ice are bubbles containing air from the past. By analyzing these bubbles, scientists can measure past CO2 levels, temperatures, and atmospheric composition with incredible precision. What these ice cores reveal is sobering. For the past 800,000 years, Earth has oscillated between ice ages and warmer interglacial periods. During ice ages, atmospheric CO2 drops to around 180 ppm and temperatures plunge. During interglacials, CO2 rises to about 280 ppm and temperatures warm. These cycles are driven by variations in Earth's orbit and axial tilt, the Milankovitch cycles, which change how much sunlight each hemisphere receives. Antarctica has been at the center of these cycles. During ice ages, its ice sheets grew even larger, pushing beyond the current coastline onto the continental shelf. Global sea levels dropped by 120 meters, 400 feet, as more water became locked in ice. During interglacials like the current one, the ice sheets retreated slightly, but Antarctica remained frozen. The ice cores show something else. The current interglacial period, which began about 11,700 years ago, should be coming to an end. Based on orbital cycles, Earth should be slowly cooling, heading toward the next ice age. Atmospheric CO2 should be around 260–80 ppm. Instead, CO2 is now over 420 ppm and rising rapidly. We've added more CO2 to the atmosphere in the past century than natural processes have in any comparable time period in at least 800,000 years. We are conducting an experiment on Earth's climate system that has no precedent in the ice core record. And Antarctica is beginning to respond. Not everywhere, the East Antarctic ice sheet remains stable and is actually gaining ice in some areas due to increased snowfall. But West Antarctica is a different story. The West Antarctic ice sheet is melting. Glaciers that flow into the ocean are speeding up, thinning, retreating. Warm ocean water is circulating beneath floating ice shelves, melting them from below. In some regions, the rate of ice loss is accelerating. Between 1992 and 2017, Antarctica lost about 3 trillion tons of ice, contributing to sea level rise globally. The Pine Island and Thwaites glaciers in West Antarctica are of particular concern. These massive glaciers are grounded on bedrock that slopes backward, meaning the deeper you go inland, the deeper the bedrock is below sea level. This geometry creates a feedback. As the glaciers retreat, they encounter deeper water, which allows more warm ocean water to flow beneath them, which causes more melting, which causes more retreat. It's a runaway process that, once started, may be unstoppable with current climate forcing. If Thwaites Glacier alone collapsed, it would raise global sea levels by about 65 centimeters, 25 inches. But more importantly, Thwaites acts as a plug holding back other glaciers in West Antarctica. If it fails, it could trigger a broader collapse of the West Antarctic ice sheet, which would raise sea levels by 35 meters, 10–16 feet, over centuries to millennia. We're watching, in real time, the beginning of a transformation. Not as dramatic as the initial freezing 34 million years ago, not as rapid as the Eocene-Oligocene transition, but a transformation nonetheless. The question is, how far will it go? Will Antarctica return to an ice-free state? Could the forests grow again? The answer to that question depends entirely on us and what we do about climate change. And to understand the possibilities and the timeline, we need to look at what the science tells us about Antarctica's future. That's what we'll explore in our final sections. What happens if the ice melts? how quickly it could happen, and whether the green Antarctica could ever return. Could Antarctica become green again? It's not a hypothetical question anymore. It's a real possibility that scientists are actively modeling and trying to understand. The answer is complex, frightening, and depends entirely on how much greenhouse gas we continue to pump into the atmosphere. Let's start with what we know from the geological record. Antarctica has been ice-free before, not just 90 million years ago in the Cretaceous, but more recently too. During the Eocene period, around 50 million years ago, after the dinosaurs, but before the ice sheets formed, Antarctica had temperate forests. The climate was warm enough for palm trees in the Arctic. Antarctica was covered in southern beech forests, conifers, and other vegetation. The atmospheric CO2 level during the Eocene was roughly 801,000 ppm. That's roughly double what we have now, 420 ppm, but it's a level we're on track to reach within the next century if we continue current emission trends. Some high-emission scenarios project CO2 levels could exceed 1,000 ppm by 2100. So we know that at CO2 levels we could realistically reach this century. Antarctica has been ice-free in the past. The question is, how quickly could the ice melt, and what would the process look like? The scientific consensus is that completely melting Antarctica would take centuries to millennia, not decades. Ice sheets are massive, and they have tremendous thermal inertia. Even if air temperatures rise above freezing, it takes enormous amounts of energy to melt billions of tons of ice. The East Antarctic ice sheet, in particular, is extremely stable. It sits on high bedrock, far from warming ocean waters in the coldest part of the continent. But the West Antarctic ice sheet is a different story. As we discussed, parts of it are already melting, and the geography of West Antarctica makes it particularly vulnerable to rapid collapse. Much of the ice sheet rests on bedrock that's below sea level. Warm ocean water can flow beneath the ice, melting it from below. As the ice retreats, it encounters even deeper bedrock, allowing more warm water underneath, accelerating the melting. This is what glaciologists call marine ice sheet instability. Computer models suggest that if we continue on a high-emissions pathway, the West Antarctic ice sheet could begin an irreversible collapse within this century. Not complete melting, that would take 201,000 years, but the beginning of a process that once started couldn't be stopped even if we immediately reduced emissions to zero. The collapse of West Antarctica alone would raise global sea levels by 35 meters, 1016 feet. That's enough to inundate most major coastal cities. Miami, New York, Shanghai, Mumbai, Lagos, all would be partially or completely underwater. Hundreds of millions of people would be displaced. It would be the largest humanitarian crisis in human history. But even if West Antarctica collapses, the East Antarctic ice sheet would remain. For East Antarctica to melt significantly, we'd need sustained atmospheric CO2 levels well above 600–800 ppm for thousands of years, combined with much warmer ocean temperatures. This is theoretically possible under extreme emission scenarios, but it would take millennia, not centuries. So what would Antarctica look like during this transition from frozen to green? It wouldn't be a simple reversal of the freezing process we traced earlier. It would be something new, something that has no exact parallel in Earth's history because the rate of warming we are causing is unprecedented. First, the coastal ice shelves would collapse. These are the floating extensions of glaciers that stretch out over the ocean. When they collapse, as several already have, the Larsen A and B ice shelves collapsed in 1995 and 2002. It doesn't directly raise sea level because they're already floating, but it removes the buttressing support that holds back the land-based ice behind them, allowing that ice to flow faster into the ocean. Next, the marine-based portions of West Antarctica would retreat. The coastline would move inland as ice melts and sea level rises. What was once buried under ice would be exposed: rock, sediment, and the fossils of ancient forests. Archaeological sites from ancient Antarctica would emerge, preserved under ice for millions of years, suddenly exposed to air and weather. As temperatures continued rising and ice continued retreating, lakes would form. Not the subglacial lakes like Vostok that exist under the ice now, but surface lakes, pools of meltwater collecting in bedrock basins. Some of these lakes would be massive. The bedrock topography of Antarctica includes deep basins that are currently filled with ice, but would become lakes if exposed. These lakes would be sterile at first, no fish, no aquatic plants, nothing but bacteria and algae arriving on the wind or carried by birds. But over centuries, they would be colonized. Microorganisms would establish ecosystems. Eventually, more complex life would arrive. Insects blown in from South America or Australia, seeds of hardy plants traveling thousands of miles. The first plants to colonize ice-free Antarctica would be mosses and lichens, the same organisms that currently survive in the few ice-free coastal areas. They can survive in nutrient-poor soil, extreme temperature fluctuations, and high winds. They would spread across the newly exposed rock, beginning the slow process of soil formation. As the climate continued warming, remember, this process requires sustained high CO2 for millennia. More complex plants would arrive. Grasses, then shrubs, then eventually trees. But here's something crucial. The trees that colonize future Antarctica would not be the same species that grew there 90 million years ago. Those species are extinct, gone forever. The podocarps and araucarias that dominated Cretaceous Antarctic forests exist today, but in different forms, evolved for different environments. The trees that would colonize a warming Antarctica would come from the nearest current forests: southern Chile, New Zealand, Tasmania. Southern beech trees, Nothofagus, which already grow in these cold southern regions, would be likely early colonizers. So would various conifers adapted to cold climates. Over thousands of years, as the climate continued warming, more diverse forests might develop. But here's what's critical to understand. Even if Antarctica became completely ice-free and forested, it would not look like Cretaceous Antarctica. The day-night cycle would be the same: 6 months of summer sun, 6 months of winter darkness, but everything else would be different. Different species, different ecosystems, a new world built on the ruins of the old. And this assumes CO2 stays high enough, long enough, for complete melting to occur. If we stabilize CO2 at moderate levels, say 500–600 ppm, we might get partial melting. West Antarctica loses its ice, but East Antarctica remains frozen. Coastal areas become ice-free and support tundra vegetation, but the interior remains an ice sheet. Antarctica becomes a hybrid, partly frozen, partly green. This intermediate state might actually be the most likely scenario for the next few centuries. Not complete melting, but significant retreat of ice sheets, exposure of coastal areas, development of tundra, and eventually scrubland vegetation in ice-free zones, while the coldest interior regions remain frozen. But even this intermediate state would be catastrophic for humanity. The sea level rise from partial melting would still displace hundreds of millions of people. Coastal infrastructure worldwide would need to be abandoned or protected by massive seawall systems costing trillions of dollars. The Antarctic ecosystem would be in flux, with no stability, constantly responding to continuing climate changes. There's another possibility that's darker still: runaway ice sheet collapse. Some models suggest that under very high warming scenarios, feedback loops could cause ice sheets to collapse faster than current models predict. As ice melts, it exposes darker rock and ocean water, which absorb more sunlight, which causes more melting. Meltwater on the surface of ice sheets forms lakes that absorb heat and drill down through the ice. Ice sheet fracturing could cause massive chunks to break off. If these feedbacks kick in strongly enough, Antarctica could lose most of its ice in centuries rather than millennia. This would be catastrophic beyond imagination: sea level rise of 50–60 meters, 160–200 feet, over just a few centuries. Every coastal city, every low-lying area, every river delta gone. Reshaped coastlines globally. The map of Earth would need to be redrawn. Is this likely? Most scientists think not. Current models don't show such rapid collapse as probable, but the uncertainty is large. We've never deliberately warmed the planet this fast before. We don't know if there are tipping points we haven't discovered. We don't fully understand all the feedbacks. We are in uncharted territory. What we do know is this: the trajectory we're on now leads to significant Antarctic ice loss. Not immediately, not catastrophically fast, but inexorably. Every year we continue high emissions, we commit to more future ice loss, more sea level rise, more climate disruption. And once started, some of these processes can't be reversed on human timescales. Even if we stopped all emissions tomorrow, CO2 stays in the atmosphere for centuries. The oceans continue warming for decades. Ice sheets continue responding to warming that already occurred. There's a lag between cause and effect that means we're already committed to some amount of Antarctic melting from warming that's already happened. The question isn't whether Antarctica will change, it's already changing. The question is how much, how fast, and whether we can limit it to manageable levels. A few meters of sea level rise over centuries is something civilization could adapt to, though at enormous cost. Tens of meters over centuries would be civilizational collapse. Complete melting over millennia would create a world unrecognizable to us. In our final section, we're going to step back and look at the bigger picture. What does the story of Antarctica's transformation, from green to frozen and potentially back again, tell us about Earth's climate, about our impact, and about what we need to do? The lessons from Antarctica's past are also warnings about our future. Let's trace the full arc of Antarctica's story, because seeing it whole reveals something profound about Earth's climate system and our place within it. 90 million years ago, Antarctica was green. Temperate rainforests covered a continent that sat at the South Pole, enduring months of darkness, yet thriving during the endless summer sun. This wasn't a marginal ecosystem barely hanging on. It was rich, diverse, stable. It had existed for millions of years and would persist for millions more. Dinosaurs browsed among the conifers. Pterosaurs soared above the canopy. Life had adapted to one of Earth's most extreme environments and flourished there. This green Antarctica existed because Earth was in a greenhouse state. Atmospheric CO2 levels of 1,1400 ppm kept global temperatures high. Warm ocean currents delivered tropical heat to polar regions. There was no ice anywhere on the planet. From pole to pole, Earth was warm, wet, and alive. Then, over tens of millions of years, everything changed. Continental drift isolated Antarctica, cutting it off from warm ocean currents. Volcanic activity declined, and atmospheric CO2 slowly dropped. The planet cooled. By 34 million years ago, ice sheets began forming on Antarctic mountains. Within a few 100,000 years, permanent ice covered most of the continent. The forests died. The animals fled or went extinct. Green Antarctica became white Antarctica. For the next 34 million years, Antarctica remained frozen. Ice sheets grew and shrank with orbital cycles, but the continent never again supported forests. It became the coldest, driest, most hostile place on Earth. Life persisted only in the most extreme forms: bacteria in frozen lakes, lichens on wind-scoured rocks, a few species of seals and penguins on the coasts. And now, in just the past century, we've begun reversing a process that took millions of years. We've increased atmospheric CO2 from 280 ppm to over 420 ppm. We're adding greenhouse gases at a rate that has no precedent in the geological record, not in speed, not in the fact of human causation. And Antarctica is beginning to respond. The West Antarctic ice sheet is melting. Glaciers are accelerating. Ice shelves are collapsing. The frozen continent is starting to thaw. What does this story teach us? Several crucial lessons. Lesson 1. Climate change can be dramatic and irreversible on human timescales. It took roughly 50 million years for Antarctica to go from the warm Cretaceous peak to complete glaciation. That's slow by any human reckoning, but the critical transition, the Eocene-Oligocene boundary, when permanent ice sheets formed, happened in perhaps 100,004,000 years. That's still slow geologically, but it represents a fundamental and irreversible transformation of an entire continent. Once the ice sheets formed, they persisted. Even during interglacial periods warmer than today, Antarctica remained frozen. The transition to an ice-covered state was essentially one way. You can't simply turn the clock back. The ecosystems that existed before are gone forever. The species that lived there are extinct. You can't resurrect a lost world. We're now engineering the opposite transition, but much, much faster. We're recreating Eocene-level CO2 in just a few centuries instead of millions of years. We don't know how quickly Antarctica will respond, but the direction is clear, and if we push far enough, the melting will become irreversible on human timescales. We'll commit to centuries or millennia of sea level rise that no amount of emission reduction can stop. Lesson 2, Code 2, is the control knob for Earth's climate. This is clear from Antarctica's history. When Code 2 was high in the Cretaceous, Antarctica was green. As Code 2 declined, Antarctica froze. The ice core record from the past 800,000 years shows Code 2 and temperature moving in lockstep. When one goes up, the other follows. When one goes down, the other does too. We've known this theoretically since the 19th century, when scientists first calculated that Code 2 should trap heat. But Antarctica's climate history proves it empirically. Code 2 controls Earth's temperature over long timescales. Not perfectly, not instantaneously, but powerfully and predictably. Right now, we're pushing Code 2 to levels that haven't existed for millions of years. We're running an experiment on Earth's climate system with outcomes that are predictable in direction, but uncertain in magnitude and timing. We know warming will occur. We know ice will melt. We know seas will rise. We just don't know exactly how much or how fast. Lesson 3. There are tipping points in the climate system. Antarctica's glaciation shows this. The climate didn't steadily cool until ice gradually appeared. Instead, the continent remained largely ice-free until a threshold was crossed. Then ice sheets formed relatively rapidly. This is classic tipping point behavior, a system that resists change up to a point, then rapidly transitions to a new state. We're likely approaching similar tipping points now, but in reverse. The West Antarctic ice sheet may be at or near a tipping point where its collapse becomes self-sustaining. Once enough ice is lost, the geometry and feedbacks make further loss inevitable. The Greenland ice sheet faces similar dynamics. These aren't gradual, linear changes we can easily adapt to. They're threshold behaviors that can surprise us. The scary thing about tipping points is that you don't know you've crossed one until it's too late. By the time we recognize that the West Antarctic ice sheet is in irreversible collapse, we'll already be committed to meters of sea level rise over the coming centuries. There's no undo button. Lesson 4. Ice sheets respond slowly, but their responses persist for millennia. This is perhaps the most important lesson. Even if we stopped all emissions today, even if we somehow removed Code 2 from the atmosphere, the warming we've already caused will persist. The oceans take decades to equilibrate with the atmosphere. Ice sheets take centuries to millennia to fully respond to temperature changes. This means we've already committed to some amount of ice sheet melting from warming that's already occurred. The question is whether we limit it to manageable amounts or let it spiral into catastrophe. Every year of continued high emissions commits us to more future melting that we can't avoid. Future generations will live with the consequences of our choices for thousands of years. The Antarctic ice sheets we lose in the next few centuries won't be rebuilt until the next glacial cycle, which, absent human interference, wouldn't begin for tens of thousands of years. We're making decisions now that will shape Earth's geography for longer than human civilization has existed. Lesson 5. What took millions of years to build can be destroyed in centuries. Antarctica's ice sheets represent 34 million years of accumulation. Layer by layer, year by year, snow fell and compressed into ice. The ice sheets are monuments to deep time, to processes operating over timescales that dwarf human history. And we're melting them. In the geological blink of an eye, we're undoing millions of years of climate evolution. The asymmetry is staggering. It took 50 million years to freeze Antarctica. It might take just a few thousand years to melt it. Creation is slow, destruction is fast. This applies beyond ice sheets. Coral reefs took thousands of years to grow. We're destroying them in decades through ocean warming and acidification. Old-growth forests took centuries to develop. We cut them down in days. Species evolved over millions of years. We're driving them extinct in decades. The fundamental lesson of Antarctica is that destruction is easier than creation, faster than regeneration. And once some thresholds are crossed, what's lost can never be recovered. You can't bring back extinct species. You can't recreate ecosystems that no longer exist. You can't reverse ice sheet collapse once it begins. So what do we do with these lessons? The story of Antarctica is ultimately about choices and consequences. The planet doesn't care what we do. It will respond to physical laws, to greenhouse gases, to energy balances. If we recreate Eocene-level CO2, we'll get Eocene-like climate, eventually. If we trigger ice sheet collapse, seas will rise, inevitably. But we still have agency. We still have choices. We can choose to limit emissions, to transition away from fossil fuels, to invest in renewable energy. We can choose to preserve what remains rather than accelerate its destruction. We can choose to leave future generations a planet that's damaged but livable, rather than one that's fundamentally transformed beyond recognition. The green Antarctica is lost forever. Those forests, those dinosaurs, those ecosystems, they're gone, buried under ice or lost to extinction. We can't bring them back, but we can prevent the loss of what exists now. We can avoid the worst outcomes. We can choose a future where Antarctic melting is manageable rather than catastrophic. Here's what makes this urgent. We are at a critical moment. The decisions we make in the next decade will determine how much Antarctic ice melts over the next millennium. If we reduce emissions rapidly, we might limit sea level rise to 1 meter or 2, manageable with adaptation. If we continue on our current path, we're looking at many meters, catastrophic for coastal civilization. The evidence is literally beneath our feet and buried in Antarctic ice. The past tells us what's possible when climate changes. The present shows us changes already underway, and the future depends on what we choose to do with that knowledge. Antarctica transformed once from green to white. It could transform again from white to green. Whether that happens, how fast it happens, and how much suffering it causes along the way, those are the questions our generation must answer through our choices. The lost world beneath the ice can't be saved, but the world we live in now still can be. Antarctica's story is our warning. What we do with that warning will determine whether future generations curse us for our short-sightedness or thank us for our foresight. The ice is melting. The question is whether we'll stop it before it's too late. Antarctica waited 34 million years to thaw. We don't have that kind of time. The choice is ours, the clock is ticking, and the ice is listening.